Have you ever actually stopped to think about what happens the exact second you type in a web address and hit enter? I mean, in absolute milliseconds, this incredibly complex, totally invisible digital metropolis just springs to life. Your data is instantly navigating these massive highways and secure checkpoints just to arrive exactly where it needs to go. It's kind of mind-blowing. So, today, we're going to explore that metropolis. This is Networking for DevOps.
Hello everyone, real quick, before we dive into the digital city, if you enjoy this explainer, please share it, hit that like button, and press the bell icon for notifications. We're going to break this whole thing down in very simple terms, completely in English, so let's jump right in.
Here is our roadmap for today. We'll be covering the basics of networking, IPs and subnets, the network models, protocols and routing, and then wrapping up with the troubleshooting toolkit.
Starting with number 1, the basics of networking.
So what exactly is a network, anyway? Honestly, at its absolute core, a network just forms whenever two or more computing devices connect to share files and communicate. This can be through physical cables or wireless signals. And when you scale that concept way up, connecting millions of these local nodes globally, well, you get the internet. The internet is, quite literally, just the ultimate network of networks. To really grasp the scale we're talking about, let's compare two main types of networks. First, you have a local area network, or a LAN. This connects computers in a really limited local area, like your home Wi-Fi or maybe a corporate office building. Think of LANs as your local neighborhood streets. On the flip side, we have a wide area network, or a WAN. A WAN extends those LANs over massive geographic areas, usually using huge optical fiber cables. So if LANs are the local neighborhood streets, WANs are the massive interstate highways connecting entirely different cities and countries together.
All right, moving right along to part 2, IPs, subnets, and addresses. Just like every house in a city needs a mailing address so the post office can find it, every single device on a network needs an IP address. And if you look closely at how it's structured, it's actually split into two parts. You've got the network ID, which tells us the specific street or network you're on, and the host ID, which points to your specific house on that street. Devices that share the same network ID can actually talk directly to each other. There's also one very special address you definitely need to know, and that's 127.0.0.1. We call this loopback, or localhost. It literally loops right back to your own machine. It's the digital equivalent of just talking to yourself, which is super useful for testing things locally without ever connecting to the outside world.
Now, as you can imagine, we have to manage all these addresses efficiently, right? We do that using subnetting. Look at this CIDR table. Instead of just handing a tiny startup a massive chunk of 16 million IP addresses, which would obviously be a ridiculous waste, we use subnet masks to carve the internet up into perfectly sized little neighborhoods. A /22 gives you exactly one single host address. A /24 gives you a nice little neighborhood of 256 addresses, perfect for a small office. All the way up to a /0, which is literally the entire internet, all 4.2 billion addresses. Subnetting is absolutely crucial because it prevents waste and keeps network traffic isolated and secure.
Let's jump into part 3, the network models.
Okay, so how does a message actually get from person A to person B? Conceptually, we use the 7-layer OSI reference model. Think of this like a giant assembly line in a factory. Starting at the top, layer 7 is the application layer. That's your web browser where you type the message. The message goes down the line, the presentation layer encrypts it, the session layer opens up a connection, the transport layer chops it into smaller segments, the network layer slaps on the destination IP address, the data link layer adds the physical hardware addresses, and finally, layer 1, the physical layer, turns the whole thing into raw ones and zeros and shoots it across a physical wire or Wi-Fi wave.
But here's the catch. While that 7-layer OSI model is fantastic for theory and passing exams, the real internet operates on something much leaner. The 4-layer TCP/IP model. It basically squashes the top 3 OSI layers into one big application layer. It keeps the transport and network layers pretty much the same and then merges the bottom 2 into a single network access layer. This TCP/IP model is the actual real-world framework powering every single website and app you're using today. It's highly practical and it just gets the job done.
Which brings us to part 4, protocols, routing, and DNS.
Our data needs a reliable set of rules for traveling, right? Enter TCP, the Transmission Control Protocol. Before TCP sends even a single piece of your data, it performs this incredibly polite 3-way handshake with the server. First, your computer sends a SYN packet. It's basically saying, hey, can we talk? The server replies with a SYN-ACK, saying, yes, I hear you, I'm ready. Finally, your computer sends an ACK back, confirming, awesome, here comes the data. This guarantees a rock-solid, reliable connection. Now compare that to UDP, another protocol that just chucks data at the destination as fast as humanly possible without even checking if it got there. UDP is great for live video streaming where speed is everything, but it's terrible if you're trying to download a critical file without corruption.
But hang on a second. When you browse the web, you aren't typing random numbers into the address bar, are you? You type words. This is where DNS, the domain name system, steps in. It's essentially the phone book of the internet. When you type example.com, your browser shoots off a query to a DNS server. If the server knows the IP address, it hands it back instantly. If it doesn't know, it will literally go ask other root servers until it finds the exact numerical IP for that domain. It seamlessly translates our human language into machine addresses in just a fraction of a second.
Okay, so you have the IP address. Now, how does that data packet know exactly which path to take through millions of global routers? It uses routing tables. Take a look at this typical AWS route table. The golden rule here is that the most narrow, specific rules are always evaluated first. For example, if a packet is aiming for a 1021 network, it stays completely local. If it's trying to hit the broader 10.0 network, it gets sent to the transit gateway. But if the address is literally anything else, it hits that final, widest rule at the bottom, 0.0.0.0/0, which just kicks it straight out onto the wild, open internet.
And finally, Part 5, the troubleshooting toolkit.
When things break, and trust me, they will break, every DevOps engineer relies on a core utility belt to diagnose the network. As your very first line of defense, you've got ping. It just bounces a quick signal off a server to test basic connectivity. If ping fails, you bring in traceroute to actually track the exact path your data is taking, hop by hop, to see exactly which router is dropping the ball. For a deeper look, netstat shows you all your active connections, while nmap maps out what hosts and services are active on the wider network. And finally, when you need to jump in and fix it, SSH lets you securely log right into the remote machine to execute your commands. These are absolute lifesavers.
So, we've gone from defining a basic network to subnetting IP addresses, navigating the whole TCP/IP model, shaking hands with protocols, and mapping the routes. Every single time you click a link, this massive, split-second coordination happens flawlessly behind the scenes. The invisible city springs to life. Now that you actually understand how these digital roads, addresses, and vehicles all work together, the real question is, what are you going to build on top of them? Keep learning, keep exploring, and I'll see you in the next explainer.